Very happy morning, everyone, students. I hope everyone is doing fine. Stay safe and healthy at home always. Make use of this time wisely for your studies. Don't waste your time. So, let's recap what all we discussed in the last class. So, last class we started with the new lesson P block elements part 1, which is your second unit. So, we all discussed with the periodic table. So that in the periodic table you can see the p block elements to the right side of the periodic table. So what is the speciality of this periodic table? Except this, all the other blocks have only metals, but this periodic table of p block elements alone, it is having metals, metalloids and non-metal. So that is the speciality of this p block elements. So we started with the general trends in the properties of p block elements like electronic configuration and oxidation state. So what is the electronic configuration for p block elements, children? Do you all remember? Yesterday only we saw. So it is ns2 np126 is the general electronic configuration. If you take the oxidation state, it is equal to that of the valence electrons of each group. Next, if you take this oxidation state, it is not available only as positive. There are negative oxidation state also. So you can see this halogens. Halogens, it is having the negative oxidation state. And what is the boron family called as? Icosagens. Carbon family, it is called as tetragens. Nitrogen family, it is called as pnictogens. Oxygen family as chalcogens. Halogens as fluorine family. And finally you will have the inert gases. Then we saw the metallic nature. So this metallic nature, what happens? As you move down the group, the metallic nature is increasing. Next we saw the ionization enthalpy. What is ionization enthalpy? Amount of energy required to remove an electron, we call it as ionization enthalpy. So actually when you take the periodic table, as you move down the group, the ionization enthalpy, what happens? It will be decreasing. So top to bottom it will be decreasing. So this is because of the size of an atom. So the size of an atom is increasing, therefore the ionization enthalpy is decreasing. But if you take the group 13 elements, from boron to aluminium alone, it is decreasing as expected. But if you move from aluminium to thallium, there is a slight difference. So why? Because it is, you all know very well, do you all remember why it is showing slight difference? Because of the inner DF electrons poor shielding effect. So I told you what is meant by poor shielding effect also compared to that of the S and P electrons. Is it clear? Next is electronegativity we saw. So what is electronegativity? Tendency to attract the shared pair of electrons. So what happens to the electronegativity? It also decreases down the group as the atomic radius is increasing. Next we saw the anomalous property of first elements of the p block. So anomalous property means what? Deviating property. So if you take group 13, boron alone, it is a metalloid. It shows diagonal relationship with silicon in group 14. If you take 14th group, the first element is carbon, which is a non-metal, and the speciality of this carbon is it has a catenating property and it can form multiple bonds because of that. Then group 14, the first element is the nitrogen. It is also having a multiple bonds, and then it can exist in diatomic gas. Then group 16, oxygen, also it can also exist as diatomic gas. Group 17, fluorine, it is the most electronegative element in the periodic table. It can show -1 oxidation state. Then we saw inert pair effect. What is inert pair effect? The NS electrons do not take part in bonding because they stay inert. If they are staying inert means they will not take part in bonding. Instead the NP electron will be lost. So the NS electrons do not take part in the bonding. So NP will be taking part instead Ns. So we call that as inert pair effect. So the example we saw was aluminium and thallium. The group oxidation state for group 13 is +3, but aluminium only it is showing +3 oxidation state. If you take thallium, it is showing +1 instead of +3. Finally, we saw allotropism. Allotropism means same physical state but different crystalline or molecular forms. We had so many examples. So in today's class, we are going to start the next part of the lesson from page 31 to 34. That is group 13 boron group elements. Is it clear? Now we are going to see under this, we will be discussing occurrence, physical properties, chemical properties and uses. So first is occurrence. So how it is existing in this earth's crust. So if you take this boron, it mostly occurs in the form of borates. So its most important ore is borax, which is Na2B4O5 OH4.8H2O, and other ore is kernite, which is Na2B4O5 OH42H2O. And next, if you take the aluminium, after boron you have aluminium, which is the most abundant metal, and it is always existing in the form of oxides as aluminosilicate rocks. The chief ore of aluminium is what? Bauxite, Al2O3.2H2O. Next, if you take the other elements like gallium, indium and thallium, they occur as sulfides. So boron, they occur as borates, and their main ore is borax and kernite. Is it clear? Aluminium will be existing in the form of aluminosilicates, that is in the form of oxides. Remaining will be existing in the form of sulfides. Next is physical properties. So physical properties will be like what is its physical state, what is melting point, boiling point, all this will be coming under this physical state. So if you take at 293 Kelvin, which means around 19.85 degrees Celsius, you can see all these boron, aluminium, gallium, indium, thallium, they all are in the form of solid, and their atomic number is increasing. So the atomic number may seem to increase, but the number of shells will not increase much because the p electrons only it is getting added. So there won't be much bigger in size difference in them. Next you have is isotope. Third row you can see isotope. What is an isotope? Same atomic number but different mass number, we call it as isotope. So boron has boron 11, aluminium has aluminium 27 isotope, gallium has 69 gallium, indium has indium 115, thallium has thallium 205, and their atomic masses are here. Next is electronic configuration. So inert gas configuration they have given here. He2s2 2p14 boron. So He means it has having 2. So that 1s2 is represented as He. Next, if you take neon 3s2 3p1 means instead of writing 10 number of electrons 10, they have mentioned as neon. So neon represents 10 electrons. Argon represents 18 along with the 3d10, 4s2 and 4p1. Krypton 36 along with the remaining electrons, and xenon will be 54 along with the remaining electrons. Next, if you can see the atomic radius, the atomic radius doesn't differ much because as I have told you, the size doesn't change too much because the p electrons only it is adding in the same shell. The number of shells it is not increasing. Therefore, there is a slight difference. There is only slight difference as you move from left to right of the periodic table. The atomic radius slight difference. Density is like for boron it is 2.34. So same way density it is increasing because the p electrons are getting more and more. So the density of the electrons is more. Melting point. So depending upon the size, like boron if you take, it is very smaller in size, its melting point is very high. Why it is very high means it will be very close to the the electrons of boron will be very close to the nucleus. They will be having good attraction. Therefore we need more energy to break that attraction. So it takes more temperature to melt. So as you move, it is decreasing, and boiling point also the same. Next is chemical properties of boron. So we are going to see the chemical properties.